All right, welcome to The Explainer. Today, we are diving into something we feel every single day, but, we probably don't think about it all that much. Heat. We're going to talk about what it is, how we measure it, and how it moves through our world in some really fascinating ways.
Okay, so let's jump right in. And we'll start with the one tool we all have for judging temperature, our own hands. But are they any good?
We all think we're pretty good at this. You touch something, you know if it's hot, you know if it's cold. Simple, right? Well, maybe not. There's this classic little experiment that shows our sense of touch can be, well, a little bit deceptive.
Okay, so check this out. Imagine you've got 3 bowls of water, one cold, one warm, and one in the middle that's just lukewarm. You stick one hand in the cold, the other in the warm for a minute. Then you plunge both hands into that lukewarm bowl at the same time. And this is where it gets weird. The hand that was in the cold water feels like the lukewarm water is warm, but the hand that was in the warm water feels like the lukewarm water is cold, even though they're in the exact same water. So what does that tell you? It tells you our sense is all about contrast, not about an actual number. Our hands, it turns out, are terrible thermometers.
Okay, so if our hands are out, what do? How do we get a real, objective number for how hot or cold something is? We need a tool that plays by the rules of physics, not by our feelings.
And that, right there, is what we call temperature. It's the objective measurement. And the tool we built for it, the thermometer, it works because of this really cool, simple property of matter called thermal expansion. And you can see that principle in action right here. You take a bottle of some colored liquid, move it from cold water to warm water, and bam, you can actually see the liquid climb up that little tube. So why does that happen? It's simple. When stuff gets hotter, it expands. It takes up more space, and for liquids in a tube, that expansion is super predictable. That's pretty much the whole magic trick behind most basic thermometers.
Now, having a thermometer is great, but for it to be useful, we all need to be speaking the same language, right? We need a standard. That's why scientists came up with standardized scales. And the big 3 you'll run into are Celsius, Fahrenheit, and Kelvin.
What these scales do is give us fixed points that never change. They're like anchors. So for Celsius, which is used pretty much everywhere except the US, water freezes at exactly 0 and boils at exactly 100. Super simple. These numbers turn that fuzzy feeling of hot or cold into hard data we can all agree on.
All right, so we've got a handle on how to measure temperature. But that just leads to a deeper question, doesn't it? What is this heat that we're measuring? What's actually causing the number on the thermometer to go up or down? And here's the key. Heat isn't a thing, it's energy. Specifically, energy on the move.
Yep, this thermal energy is never sitting still. And it follows one super simple, unbreakable rule. It always flows from something hotter to something colder. Always. We call this process heat transfer, and it happens in 3 totally different ways.
And here they are: conduction, convection, and radiation. Don't worry, they're simpler than they sound. And these 3 methods, they basically run the world. From the stove in your kitchen to the sun warming the whole planet, it all comes down to these 3.
So let's dig into each one. We'll see how these 3 paths show up in our everyday lives, in everything from a spoon in your coffee to the wind at the beach.
Okay, first up, conduction. This is heat moving through direct touch. The way to think about it is like a chain reaction. Imagine all the tiny particles in a metal spoon are lined up. You heat one end, and that first particle starts jiggling like crazy. It bumps into its neighbor, which starts jiggling, and bumps into its neighbor, and that energy gets passed right down the line. That's conduction. And it's exactly why the handle of that spoon gets hot when you leave it in your tea. This is a fantastic way to actually see conduction happen. You've got a metal rod with a few pins stuck to it with wax. You heat one end with a flame and just watch. As that heat energy travels down the rod and melts the wax and the pins start dropping off, one by one, from the hot end to the cold end, you're literally watching the heat move.
But here's the thing. Not everything is a good conductor. And we use this difference to our advantage all the time. Materials that let heat zip through them easily, like metals, we call those conductors. That's why your frying pan is made of metal. But materials that are really bad at transferring heat, like wood, plastic, even air, we call those insulators. They're just as important. That's the plastic handle on the pan, or the puffy winter jacket you wear. It's all about controlling that flow of heat.
All right, next up is convection. Now this one is all about heat transfer in fluids. And when I say fluids, I mean liquids and gases.
Unlike conduction, where the particles just kind of vibrate in place, convection is all about big movements. So here's the breakdown. Think about a pot of water on a stove. You heat the bottom, right? The water down there gets hot, it expands, and it becomes less dense. Basically, it gets lighter. So what does lighter stuff do? It rises. As it rises, the cooler, denser water from the top sinks down to take its place. Then it gets heated and rises, and you get this constant circular flow going. That, my friends, is a convection current. And if you want to see a convection current on a massive scale, just look at the beach. During the day, the land heats up way faster than the water. So the hot air over the land rises, and where does the replacement air come from? The cool air from over the sea rushes in. That's your sea breeze. Then at night, it flips. The land cools off faster, but the ocean holds its heat. So the warm air over the water rises, and the cool air from the land flows out to sea. A land breeze. It's a giant convection engine powered by the sun.
Okay, last but not least, radiation. Now this one is really special. It's special because it doesn't need any stuff to travel through. No particles, no liquid, nothing. It travels as electromagnetic waves, just like light. Radiation is how the sun's heat makes it all the way across the vacuum of space to Earth. It's also how you can feel the warmth from a campfire, even if you're not touching it and the air isn't blowing on you.
And when it comes to radiation, the surface of an object makes a huge difference. Check out this experiment. You've got 3 cans out in the sun. One black, one white, and one shiny. Which one do you think gets hottest? The black one by a long shot. That's because dark, dull surfaces are amazing at absorbing radiation. Lighter, shiny surfaces, they're much better at reflecting it away.
And we use this idea constantly. Why are houses in hot, sunny places so often painted white? To reflect the sun's radiation and stay cooler. And that shiny emergency blanket? It's not creating heat. It's a mirror for thermal radiation. It reflects your own body heat right back at you, which is what keeps you warm. Pretty clever, huh?
Okay, let's pull all these threads together now. We've talked about temperature, conduction, convection, radiation. So what? Why does this stuff actually matter in the real world?
So if there's one thing to really get straight, it's this. Temperature and heat are not the same thing. Temperature is just the measurement, it's a number. Heat is the actual energy that's moving around. And now you know the 3 ways it moves: through direct touch with conduction, through flowing fluids with convection, and through waves in space with radiation.
Once you get these basic rules, you start seeing them everywhere. You can explain so much about the world. So, I'll leave you with a little challenge. Now that you know the rules of the game, how would you design the perfect coffee mug? One that keeps your coffee hot for as long as humanly possible. Think about it. What materials, what shape, what colors would you use to defeat all 3 types of heat transfer? Something to ponder over your next cup.